obviously. 1 over k factorial. Because 2 is equal to 2 factorial, so proved, right? No, I mean, you have to think about rearrangements. You know, if you think about, well, to actually prove that, you need something like this. Can I erase this? Let me erase this. For me, when I try to prove something like that, the main thing I use is this, guys. This is my anchor. My excuse to get away from combinatorics, basically, is this dxi1 wedge, wedge dxin, ik rather. This is just epsilon I1. That can't say that either. Curse as well. And so you just kind of like take anything like that and rewrite it. I'm not making any sense, guys. Let me shut up. This is not helpful. I'll write some homework problems. That'll fix it. Okay, so anyway, admittedly, there's a gap. I showed you for k equals 2. I haven't showed you for k. I admit it. You got me. But the larger point is I can rewrite a differential form. If I don't want to use increasing indices, I can take the sum over all indices, and I just have to put this 1 over k factorial if I want to be consistent. And that's nice, because then if I take the exterior derivative of alpha wedge beta, right, and if this is a k form and that's an L form, then what I'm looking at is the exterior derivative of the sum, right, notation. Let me just leave the alpha. Eventually I'll get it. 1 over k factorial, 1 over L factorial, alpha I1 ik, beta J1 JL, and then dx I1 wedge wedge dx. I don't know, why am I not using multi-index notation? What's wrong with me? I introduced it so I didn't have to write this. I can't follow my own thinking. Anyway, so the exterior derivative of all this, which I should be more civilized and just refer to this as dx I wedge dxj perhaps, right, to save myself so stupidly much writing. And this is equal to the sum over, and so I really should be careful not to, well, so if I just say sum over I and j, if we want to, we can understand that to mean the sum over all indices. But I should be careful. If I'm going to do that, then I shouldn't write these. I can't have this is increasing and that's, I got to make some kind of notational choice and distinction here, so I don't know. Until I make up my, good grief. Should we, what do you guys want to do? So I sub k is not increasing, it's just the set of all k indices? Yeah. Okay, you've made this unwatchable for future generations, but I like it. Anyway, the point is, this is the sum. Fine, let me just, you know, sometimes you just got to do some writing. Hey, if you want to declare your notation to mean a certain thing, just declare it and I'll read it. You know, it's cool. Sum over all indices. 1 over, I really should not, let me shut up. And then the exterior derivative of this, right? You know what? I'm going to use some writing. I, j, all values. all choices. There we go. I need some stupid notation for it.
Go back to 2 years ago.
7. Joe is still here. Stupid Joe. See your DXI. All right, I will be inconsistent. You know what? I'm going to be inconsistent. There we go. How about this? Let us agree on this. If we're going to use increasing indices, we must declare that I is an element of the increasing, j is the element of the increasing indices of length L. And so here I is an element of the increasing indices length k. So I just tack on this back there, and now I have my freedom to be all freewheeling and not worrying about increasing indices because it's a drag. I'm sorry, I was hoping this lecture would not devolve into this. I'm gonna get it though. All right. Now that we have settled our notational demons, the proof is stupidly easy. See, because this is a function, this is the total derivative of a function, and we have a product rule for that, like calculus 3. I mean, if you want to, I can expand this explicitly. This is the sum over j, right, equals 1 to n of partial alpha I beta j partial xj dxj. I mean, that's the total differential of that. And so you can do the product rule on that, and it gets you to this. Sum over I big J little j 1 over k factorial L factorial. We've got partial alpha I partial xj dxj beta j plus alpha I partial beta j partial xj. I'll put some big parentheses here, dxj, wedge dxi, wedge dxj. Man, I'm glad I stopped writing those indices out. Yep. And so there we go. We got ourselves an I, we got ourselves a j, and what I'm gonna do is I'm gonna go ahead and I'm gonna keep the where was I? Curses. I'm getting to it. All right, I actually need to do some thinking for the next step. So, all right, we want to rearrange things a little bit. Look at this. The sum over j here, little j, and it's got an I attached to it, right? So I'm stuck with that I. And that I goes with the alpha, which goes with the k factorial. So I take the sum over I. We got our 1 over k factorial. We got our sum over j equals 1 to, if I was smarter, I'd done a lemma, you know, and I would have proved the zero form lemma, like in the book. But on the other hand, the book's dumb, because book doesn't believe in multi-indices. Not really. Not like I do. Let's see here. And then that's the wedge with the sum over j of beta j dxj, yeah? That, see what I did here, that makes sense if you think about it. I'm missing a what? L factorial. So that's just this term. So what's going on is I can pull the big J index sum over to here because this has no big J dependence. So using properties of finite sums and the distributivity of the web product, I can bring that over to there like that. And I do the same, but I can't quite do the same calculation on the other piece, right? See what the noise is, the static over here is, yeah, I've got, the thing is over here, see what I have to do? I have to bring this over to there for that. So how's that work? You got dxj, wedge dxi, And I want to rewrite that as, let me be more explicit. That's dxj wedge dxi1 dot wedge dxi. How many are there? K? K, right, yeah. So if I want to bring this over to the other side, how many flips does that cost me? Right, minus 1 to the k. So in fact, that's minus 1 to the k dxi wedge dxj. So that minus 1 to the k term appears because I have to push this differential past the dxj coming from the total differential of the beta j. So what I get is a plus minus 1 to the k sum over I 1 over k factorial alpha I dxi wedge sum over j equals 1 to sum over, well, the j and the j. Sum over j and stink. Sum over j, sum over little j, partial, why didn't I project this? What's wrong with me? Beta j, partial xj, dx j, wedge, dx, big J. All right, can we see what's going on finally? What was this? This is d alpha. Actually, all of this. This whole thing is d alpha. This is beta. This is alpha. This is d beta. And so we have that. We have the graded Leibniz rule for wedge products. So d alpha wedge beta is equal to alpha, or rather d alpha wedge beta minus, or rather plus, minus 1 to the k alpha wedge d beta. There you go. That's how we derive the graded Leibniz rule for the wedge product. The book doesn't really believe in my notational scheme. I mean, he has lots of, he does some sums, but he also does a lot of plus dot dot dotting. You don't really see me doing plus dot 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 at all, do you? No, not a thing. Yeah, so I believe in the indices. Now, let's see here. So I think I'm trying to remember. What's the relation of this and, like, what about d squared equals to 0? Can we prove that? dd alpha. What would that be? Let's actually work that out while we got this kind of monstrous formulas in front of us. Let's get into that. So if we were to try to calculate dd alpha, what would that look like? Sum over I, right, of d alpha I wedge dxi, right? Which then looks like what? Well, I can't really do it, can I? I guess I got to kind of unwrap that a little bit, don't I? I comma j, let's say, partial alpha I, partial xj, dxj, wedge dxi. And let's put a 1 over, what do I want, k factorial? Since I'm not working with increasing indices. See, the alpha sub I has a fixed meaning. Because it has a fixed meaning, I have to put that 1 over k factorial. Otherwise, I'm being inconsistent with our larger program of notation. So the meaning of alpha sub I is fixed by our choice of basis of increasing forms. I will try to give you homework which helps you understand that, not for a k form, but for like a 2 form. Because if you can understand it for the 2 form, then there's no sense in... If you can understand it for a 2 form, you understand. Let's just say that. Anyway, so this would then be the sum over I, let's say j, and I need another index, let's say m, right? 1 over k factorial, and then I've got partial squared alpha I, partial xm, partial xj, dxm, wedge dxj, wedge dxi. I'm sorry, poor Kang. He's getting his sun for the day. Should have moved the camera. So this we have to apply to like a fundamental lemma of tensor arithmetic, which is that if you've got a sum, right? If you've got a sum over, say, j and m, and you have something that's symmetric in indices jm, and you have that contracted over something that's antisymmetric in the indices jm. So here I mean that s jm equals to s mj, whereas a jm is equal to minus a jm, mj rather. Well, you see what happens is if you relabel the sum, let's say, no connection with the k and l over here, but k and l, you know, then I can flip them. Right? And then relabel them back again to jm. So we've showed that this is equal to minus that. So it's 0. It doesn't matter what else is floating around there. If in the summation that you're looking at, if there's a pair of indices, and the object you're summing over has those indices appearing as symmetric against an antisymmetric, when you calculate that contraction, it has to be 0. And that's what's happening here. See, this is symmetric, right? In m and j, right? Whereas this is antisymmetric in mj. So that works out to 0. Now the book says if you can do it, if you have this for 0 forms, then you can get it for k forms by using the graded Leibniz rule. I suppose that makes sense, right? Do you see why that is? If we knew it for 0 forms, if we have d of d alpha, it's what? Well, what else is there? If you're taking the, so think about this as being your alpha, and this as being your beta. So what else is there? There's well, I should say -1, right? I guess to the k plus 1. That's alpha I. I guess that's just -1. That's a 1 form, right? D of dxj. So see, if you, is this 0? You can calculate this is 0 by a short calculation. It's not hard to see that this is 0. Its coefficient functions are constants. So its exterior derivative is 0, essentially from the definition. And this is the d squared on a 0 form. So the book says that if you can prove d squared is 0 on a 0 form, that paired with the graded Leibniz proves d squared is equal to 0. I say, that's great, wonderful, but I can also prove it directly by the tensor calculus. So whatever floats your boat, I mean, yeah. So I think we're about to where we got last time, except now we've leveled it up to n dimensions and we actually constructed a wedge product today, right? And I've opened Pandora's box of interesting matrix linear algebra questions, right? Like, there's got to be interesting homework questions I can ask you about proving things about determinants using wedge products, or vice versa, right? I'll try to think of an interesting one of those if it's not already in the book. Next time, we will look at further calculations with differential forms. Like, the next thing we need to talk about is the pullback, right? So the pullback is this. If you have a function that goes from a manifold to another manifold n like that, and if I have, say, alpha, an element of the wedge products, excuse me, the dual forms on n, then I can talk about the pullback of alpha as being a k-form on m. And the way you do that is you apply, well, he has the linear algebra of it in the section I was expositing earlier today, but the definition is just this. If we take f pullback alpha, we have to make it a k-form over here. That means it has to be able to act on v1 vk, and these are in the tangent space at a point p, let's say, to m. Right. So technically, this is at p. And I mean, I suppose technically, let me not. Okay. Anyway, getting to the point. This is going to be alpha of something, right? So I'm trying to define how you construct a k-form on m from a k-form on n. So this alpha eats n vectors, tangent vectors to the manifold n. But my inputs are tangent vectors to the manifold m. So what do you think we do? Apply f to each. Almost the right idea. He calls it f lower star, right? F lower star p of v1, f lower star p of v2, f. Now, just to be asymmetrical, I called it d sub pf of vk. So you push forward. You just push forward your k-tuple of vectors. You can use the push forward, the abstraction of the differential on the manifold. That will take your tangent vectors at m to corresponding tangent vectors at n. And so we have a way of pulling back a differential form. But look, guys, for example, you could have like yx, and over here you might have r theta, right? And you might have the mapping maybe this way, right? X equals to r cosine theta, y equals to r sine theta, something like that. If you look at, let's see here, if you look at dx wedge dy, and if I call this mapping f, right, the pullback, when we actually get into the details of this, the pullback of dx wedge dy, you know what it's going to be? It's going to be nothing more than like d of r cosine theta wedged with d of r sine theta. That's actually that's what this pullback is actually doing. It's like taking the form in the codomain to the corresponding form in the domain with respect to the transformation. If you apply it to the case of a space mapping to a space, it's actually just sort of coordinate change of the form from one coordinate system to another. But we'll do a bunch of calculations next time, so it makes more sense and so forth, but that actually is what this definition sorts out to mean at the level of intuition. But anyway, I shut up. We'll talk about, this is what we're going to talk about next time for a long time. So, and then if I play my cards right, we'll do that, and that'll be a good setup for the end of next lecture to do the, well, next lecture I really should talk about pullback, the integration of differential forms over manifolds, and if I say my words correctly, hopefully the Poincare conjecture, which is an explicit calculation that combines those two ideas to do something interesting. So, but that might take me all week. I'm not going to hurry it. We'll play it by ear, see what happens. I owe you guys homework, of course. I will eventually write it and send it to you. But in the meantime, relax. Take my time. I heard some of you have some jerk giving you an abstract algebra test soon, so some jerk. I heard that the topics are kind of hard right now. I don't know. A little bit. Anyway, thanks, guys. Oh, I meant to do that. I'm sorry, Travis. I had, that was on my list of things I was supposed to do before class today. And then I had this most annoying and egregious waste of my time called the math. And then Dr. Sperano came and talked to me. Anyway, I just didn't do it. But hopefully by Monday.
I mean, if you want, you can all just take it home.
But I should actually write a solution for you guys too, because at some point there will be a comprehensive final, and you know, if I don't write a solution, it's no good.
Yeah, that's fine too.
Yeah.
Have a good weekend.
You too. Uh-oh. Yes.